Well, modular forms were instrumental in number theory in many ways, and today I would like to describe how the modular forms entered the analytic number theory and shaped shaped the analytic number theory today, and also would like to express some perspectives for future developments. Oh, that's my problem always. Yeah, there's no volume control here. Pardon? Yeah. I'm sorry. I'm afraid I'll be screaming and that. Otherwise, okay. I'll try my best. Okay. So this is extraordinary meeting, and I was listening last week lectures and was amazed with some enthusiasm how people were encouraged to talk, speculate beyond just flat theories. So understand that we actually here are allowed and even maybe encouraged to speculate. So I will try to do some speculations also in this lecture, which I have a little hesitation, but because of the nature of that meeting, I hope you will also understand that. So this is a very short lecture, so just in case I run out of time, let me say what I intended to say, and I doubt I will be able to cover everything, so at least you will know what was missed. Yeah, well, that's right. The last part is the most speculative. Come here, please. Come here. You will see everything. Yeah. You're hearing. I'm not sure if this is better. Pardon? Better? Better? Okay.
Good luck.
Okay, I try screaming. Okay, so if I don't say anything about the last section, I hope there'll be some other time in corridors with coffee talking, or maybe Peter will allow me to talk something about this in the discussion session. Nevertheless, I try to go up to that anyway, but I doubt I will make it. Anyway, so I would like to leave the impression what automorphic forms did for analytic number theory, and it's a huge territory, difficult to. There is no point to even start. You don't know from where to start. So I believe the best quick understanding would be just present first something simple, something that is not necessarily at first glance at the center of the theme, and then extend this by analogy. So I would like to first speak about GL1 harmonics. Not that of course, that will means that I will spend a little bit more time for something that is not directly related, but I think analogy I think I will gain time by just showing analogies rather than defining precisely concepts in GL2 theory. So analytic number theory is not, of course, defined precisely what it is, but more or less it is the theory of arithmetic that in which we use analysis, not only complex function theory as classically it is described, but also, first of all, harmonic analysis. So the fundamental thing that we try to do is count integers. So if you have a simple model, it's just count integers from 1 to x. The number of integers is about x, and the error term is bounded. More precisely, the error term is fractional part of x. And the best bound of this is 1, and nothing better can be done. But unfortunately, this is not a good precision for most counting that we would like to. use this simple-minded method. So what we do, just a fractional part extent is a periodic function. We just use Fourier expansion, and it is particularly good when we have many variables. I mean, when we are dealing with lattice points in a Euclidean plane, and so we can just do counting one direction at a time. And so so the expansion into Fourier series of the fractional part leads to exponential sum. And let me just jump quickly. Generally, the exponential sums that appear in problems are like over there. There's an n variable summation, and we have some nice functions of Schwarz class. GM is just simply, smoothing test function here, but the essential part is this exponential. This is E of z, this is this additive character. And what we are looking for is non-trivial bound, sometimes very good bound, depends on the problem. But the challenge is to get non-trivial bounds for such a thing. That means exploit the possible cancellation of terms due to the variation in the exponential sum here. Take, for example, a Gauss circle problem. That's just lattice points counting in a circle, and you can just, for example, freeze one variable and count the number of integers in one direction, and then just add the error terms, and the total error term would be just comparable with the circumference of the circle, the length of the curve, and that would give you error term in counting x to 1/2. However, if you use a little bit better the Fourier expansion and then for summation formula, whatever it is, you can end up with better error term because of the non-trivial bound in the exponential sums that are involved, and you get something like x to 1/3. More to the point that I'm going to make soon is to consider this problem is better look at this way. X is G is the group of translations, acts on itself, that means on X by translations, and so we are having here a homogeneous space, and phi sub m of X is the eigenfunctions of the Laplacian here. These are these additive characters here, the inner product. And as everybody here, of course, know very well, the Fourier expansion for the periodic function is just spectral resolution of the Laplacian on the torus. And we have one great instrument to study such sums, the Poisson summation, which really should be interpreted as trace formula. It's hard to admit for beginners because you just see terms on both sides of the same type. Well, because the somehow dual points to the lattice is a dual lattice here and have the same nature, So F goes into Fourier transform. So that's the Poisson formula, which is instrumental and very helpful. This would be the additive, so to speak, additive part of number theory using Fourier analysis on torus for periodic functions. And long before even that, there was a multiplicative version of analytic number theory developed by Dirichlet. Amazingly, the harder part was developed earlier than the easier one. I mean here the multiplicative characters of Dirichlet, characters modulo Q, and these are very good to pick up numbers in the sequence that we consider the numbers in a given progression. Particularly, it was designed by Dirichlet himself to pick up primes in arithmetic progression. Primes are multiplicatively defined, so Dirichlet character, the earlier additive characters are inadequate for such a thing, like picking primes in arithmetic progression. If this is the counting function, we usually count primes with with weight which is log p for simplicity. Prime number theorem says that if residual class is prime to the modulus, I mean every residual class prime to modulus has the same right, captures the same proportion of primes, so it's x over phi of q of them by prime number theorem. And let me just quickly say a few words here, how you develop this in terms of L function. You just pick up the congruence by this orthogonality property using characters, and eventually end up with sum of the primes, and the character sum of the primes. Now the primes are related to all integers by Jaeger factorization theorem, which here is realized as the Euler product for the L function. And now the explicit formula in terms of the zeros of L function says that such a sum is equal to sum over the zeros of L function. There's a main term here. If the character is principal, otherwise there's nothing here. And there are some other debris, small things here. And if we assume Riemann hypothesis, as we all believe here, there'll be heated discussion, I think, about this in days to come. All these zeros are on the critical line, and there are not so many of these zeros. So when you estimate these things, you get error term x2½ plus epsilon, and it's actually equivalent to the Riemann hypothesis. So that's what Riemann hypothesis would give for prime arithmetic progression. Of course, Dirichlet got much weaker results, yet still, existence of prime arithmetic progressions was proved by him by weaker methods. Anyway, I'm not making a point here that this result, which follows from Riemann hypothesis, is good only for q less than x2½. That means it's meaningful because the main term does not, the error term does not exceed the main term. So this is a good uniform in Q. Where is the dot? Yeah, here. Q less than x2½. And have this in mind because I will refer to this later when it comes to modular forms. Well, to show some advantage of other harmonics to play. And so that's the best possible by the Riemann hypothesis. One shouldn't forget that the function do have zeros on the critical line. I mean, so 1/2 is best possible. And some investigators, when they study, they make some testing of what they have, they forget that simple fact. This is related to somehow other philosophy, number theory, that whenever you have some kind of random oscillatory sums, you would like to have a lot of cancellation, but please never assume that you get more than square root of the number of terms of cancellation. This is almost an axiom. If your program requires better than that, you probably give up on this. So there is some, of course, we often need even more than that, but not because of the cancellation, because of other structures that appear. Okay. So quickly again, just to find the time. Let me just quickly say something about what we know about the cell functions. So the zero-free region is for the cell function rather not impressive. We know that the cell functions do not vanish when S is sigma, the real part of S is larger than 1 over constant over log of the conductor, and even that is not completely known. This is known for all the functions except for 2 of modulus q, except possibly for one simple real zero, which corresponds to real character, and this would be the Jacobi symbol. Assume q is square free. There are a few variations of that. I see that Dan may be complaining, but I'm back here. Okay, there are other yeah. What about, yeah, okay. So let's see so this is simply for the real character, which is essentially a Jacobi symbol. So this leads to a definition, a really vague definition of Landau-Ziegel zero, which says that this is a zero of such a function which is larger than that 1 minus constant over log q. Of course, we all believe it doesn't exist, but yeah, big but, yeah. So what we know, nevertheless, that even this exceptional one, which is so bad, is not too bad. Landau succeeded to prove that it is less than 1 minus constant over q2 minus 1/8, and Ziegel, half a year later in the same journal, not referring to Landau, by the way, at all, proved a little bit better that for any epsilon, you get this bound here with the constant, which does depend on epsilon, but unfortunately the constant is ineffective. And effectivity here was a big theme for of conversation, discussions before. So maybe I should stress how how terrible it is to have a result like this, which is ineffective. The Landau-Ziegler zero problem is one of the fundamental problems, unsolved problems in analytic number theory, and it's related to many things like class number problem for quadratic fields. I'm sorry, I don't have much time to say about this. This is a beautiful area, but I have not much time to talk about this. And ineffectiveness is something intrinsic in the proof. That's not just. One should be very careful with ineffective results. The way it's proved is that uses some kind of repulsion property of a zero. If there is a bad zero close to 1, it likes to be alone, doesn't like anybody around, so it repulses everyone else far away. And so when you assume there exists such a zero, you are proving that others are so far away that they are even better in the zero region than described here. So that's where the ineffectiveness comes, because if there is no such a zero, there's nothing to prove. If there is, we have a repulsion, and they just make the constant depending on this hypothetical zero. Well, again, maybe a little bit joke about is in place now. When you talk about ineffective results, let me just show you how useless could be some ineffective result. This one would be very useful, actually. But okay, here's a proposition. I mean, there exists. We don't know the Riemann hypothesis probably cannot be proved or disproved by computers. But think of this: there's a constant, let's say t, such that if the first t zeros of the Riemann zeta function are on the critical line, then all of them are on critical line. So this is ineffective result and completely useless. So but however, Ziegler's theorem, Ziegler-Landau theorem, is extremely useful. Actually, it leads to prime number theorem. That is uniform with the modulus up to log q of 2 power x. We can't really we can't really cultivate analytic number theory without this theorem. It's extremely vital theorem, though it looks like rather weak, and it's ineffective. The constant, the a is clear. Anything, the implied constant depends on a. Okay, now coming to the characters, they have very nice harmonics to detect progressions, particularly from structures that are multiplicative. They're useful because of multiplicative nature of the characters themselves. But and orthogonal in a way, because of but the orthogonality is really much stronger than you think from the group theory point of view. One should really start drifting away from. I mean, shouldn't insist that everything has this beautiful, neat, elegant structures, homomorphism here and there. Actually, characters behave much better if you start mixing the modulus. And so, if you go to primitive characters, you have the large Schiff inequality that, due to Bombieri and many others, developed on the basis of some ideas of Linig. Which says this much. I have no much time to digest this here, but let me just tell you that it is very strong, much stronger than orthogonality I said before. This is true for any complex numbers an, and in practice is a perfect substitute for the Riemann hypothesis. So in a way, we have already in 1965 result, which is for practical purposes, together with this Ziegler-Barfish theorem here, it is good to replace Riemann hypothesis. So those who prove Riemann hypothesis may be disappointed. Not many new applications. Of course, there's needless to say that we would like to see Riemann hypothesis proved rather than anything of this so far established. But people were smart to find roundabout methods going away from Riemann hypothesis using fantastic substitutes. Here is the one. Okay, so that's about GL1 harmonics, so to speak. And let me go into GL2 harmonics. There. How I call them harmonics is perhaps cryptic and not be seen before the end of the lecture, or maybe not at all. So let's make a quick jump now and go to GL2 theory. So now instead of translations, we have group SL2R and take a homogeneous space. We divide by maximal compact group. That's upper half plane. Let's use rectangular coordinates for this finite number theory. That's the best ones. Though it's sometimes polar coordinates are better. And here it is end out with this point parametric, given by this differential form, and this is here the invariant measure, the Laplacian is here, and the basic eigenfunctions can be computed in the rectangular coordinates using separation of variables, and we end up with a function. Yeah. If it is too fast, please excuse me, but that's not really the big point. Pardon?
No, this is just wrong. It's y squared.
Where is y squared? Here. Okay. All right. Yeah. Yeah. I was in this business too long. Yeah. All right. Y squared. Okay. So but it's y minus the. Okay. Fine. Let's go. So now take a discrete group. Which is finite covolume. Well, let's not be extremely general. Think of modular group or congruence group. That's good for arithmetic enough, you know. And take functions from upper half plane which are gamma periodic. Call them automorphic functions. So they really live on the quotient space. And now let's look at the spectral resolution of delta. This is self-adjoint or has actual self-adjoint extension to the L2 space on the fundamental domain. And so let's look at the resolution of delta in that space. So Fj, the Laplacian has a point spectrum, which the bottom is 0, that corresponds to the constant functions, and the other, for this congruence group at least, we know are Caspital forms. I will come to this in a moment. There's also a continuous spectrum which doesn't play a great role in my discussion here, so I just ignore it completely. Just say that this continuous spectrum is spanned by eigenpacket of Einstein series on the critical line. And in case of congruence groups, as we are interested, continuous spectrum is not a mystery at all. It is a great interesting issue in general. It's Peter and Phillips. Peter, Sinai, and Phillips would tell you more about that, but on the other occasion, I think. Okay, so cusp forms from the point spectrum has this Fourier expansion, has no constant term here, and let me just, for your intuition, tell you how many of them are there. Number of spectral parameter. It is typical to write spectral parameter this way, and the number of spectral parameters up to t is about t squared times the volume. So that's a lot. I mean, much more than for the Riemann-Zeta function, which is t log t. You see, and these points satisfy Riemann hypothesis. That means they are lying on the critical line, or there could be some between 1/2 and 1. The conjecture says of Symplectic that there are no such things there. Here, I may come to this or not. I don't know yet. Okay, so you have an idea that you have about t squared of such guys, a lot more than the number of zeros of the zeta function. Amazingly enough, or frustratingly enough, I don't know, is that for the simplest possible group, the polar group, we never even have seen a cast form written down. You know, but we know existence implicitly by counting process. That means by applying trace formula, Selbach proved. There are so many of them, just t squared times the volume. It's a very long. So here's another example why counting has some advantage in really constructing things. Okay, so for arithmetic, we would like to have only a very special basis of forms, which is extremely important, those which are Hecke eigenfunctions. So there is a bunch of Hecke operators, a sequence of Hecke operators. To save time, I don't define them here. Just leave. Okay, and they are self-adjoint, mutually commuting, and with the Laplacian, you can diagonalize the space simultaneously and pick up a basis of eigenfunctions f. At least for n coprime q, and when you do so, the Fourier coefficients in these mass waveforms are actually proportional to the Hecke eigenvalues. And because of this diagonalization, we gain some extra property of the Fourier coefficients, that is multiplicativity. Only here we can speak about L functions. I would really I would not be promoting L functions for arbitrary basis. L function has to have Euler product. So here, because of the Hecke basis, the corresponding L function to this mass form F has Euler product actually. And these guys are really independent, not only linearly independent, but in a strong spectral sense, that is, they satisfy similar inequality like lattice inequality before, even though I think it's much stronger one. So that if you have L2 estimation for this linear form in these eigenvalues, and you sum over of the spectrum, you get this bound. So because you have many more relatively to the conductor of the function, many more such functions, such lattice inequalities is much more stronger than before we had it for GL1 objects. And as you can imagine, it's harder to prove as well. But it's true. Okay, so just to say, well, to convince you that they are stronger, let me just give you an example of one application, the one that I already actually mentioned, the primes arithmetic progression. That's very central in number theory to understand how primes are discrete arithmetic progressions. They're fundamental to construct many other things. So remember, theta x q a was the counting function of primes and progressions. The main term expected was x over phi of q. And now we are also interested in averaging over the modulus up to, let's say, capital Q. And we introduce certain weights and get the bound of that size, x over log x to the power a.
You want absolute values?
No. Well, there are some with absolute values too, but I just pick up one result, which is the strongest. And I have no really time to talk about everything. So here, psi of q is a certain function bounded. I'll call it well-factorable function from the sieve theory. Never mind the concrete definition. Let's just take my point that in applications, that's what it appears in such a function there. So it's practical weight here. The point really is that you can go with q up to x, let's say 4 over 7, and it's larger than 1/2. So you see, and this is non-trivial in that range. I mean, if you just digest this a little bit, start to analyze, you see you really have to get cancellation of the error terms strong enough in order to get the things. And the Riemann hypothesis does not give you this. Riemann hypothesis, as I mentioned before, gives you only x2.5 for this, and that's too bad. If it's x2.5 times q is limited by x2.5 already. And we went up to x2.47, and never mind the exponent, the fact is that you go beyond the Riemann hypothesis. And here maybe my lecture actually should start from this point. How modular forms really enter analytic number theory. Here's maybe interesting point to make. The whole thing is that if you study primes, at least on that level, you are thinking of some kind of analysis, harmonic analysis, like additive characters, multiplicative characters. But the truth is that none of them are adequate for the whole picture. You know, there are hidden structures there. So if you use some combinatorial decomposition of some of the primes that go, I mean, this is vague. I mean, you please excuse me if you don't understand. But maybe from just writing you have an idea what I mean. So some of the primes is replaced by some of the all integers, and then some of the double sum, which is binary form. So and so the combinatorial argument, exclusion inclusion principle. You know, from prime you go to all integers and then subtract composite numbers. This is embarrassingly simple argument. It's very powerful actually, because in one range of the composition, you apply GL1 analysis when you are talking about primes, and when you're having Balna form, you're applying GL2 analysis. You just couldn't do that there, the things. And how it enters the GL2 analysis, again, very vaguely. You see, interpret the congruence Mn congruent to A mod Q as the equation, Mn equal to A plus QR, and then see this is determinant equal to A. SL2Z has determinant 1, but if you act by Hecke operators, you pick up determinant A. So you see, the problem really is here to evaluate, to solve the determinant equation. And now you can believe that SL2Z start here playing a role. It's a counting point on this surface of determinant surface. And as you should use adequate analysis to do so. For it. I mean, of course, you can force yourself and use GL1 analysis twice iterated, and that means abelian harmonic analysis. And it does produce some result, but not strong enough. You see, so this is the way that a non-abelian harmonic analysis sneaks into the field, because the determinant equation counting points of orbit of a modular group or whatever group will be there is on one side, geometrical side, the other side, from the.
You use it only if you take summation over Q also.
Yes, voila, right, good point. But there is other more important difficulties here. You know, I said that this is binary form. Alpha n, beta n are complex numbers or real numbers, but very ugly looking. And also Q is weighted by this psi of Q. So this is not a pure determinant equation. It has a lot of constraints. But there are mechanisms in that number theory I don't talk here, very ingenious actually, to get rid of these conditions, or actually to trade them for congruence conditions. And as a result, you end up with congruence groups. And that in turn leads to other great problems about small eigenvalues. You know, small eigenvalues may exist, we believe that do not, but so far we can't eliminate them. And they play the same devastating role like lambda Ziegler zero in GL1 theory. But there are lots of results about this small eigenvalues, statistical density theorems, and also very nice individual estimations that recently Rudnik and Peterson proved result beyond what was known before. And the point is that they're using fantastic analysis of GLN, not only GL2, and also Riemann hypothesis for varieties, etc., etc. So things, I mean, everything goes into this big picture, but there's no, I have to keep track of one thread here, so I will not ramify into these things, but there's a fantastic analysis. So at least I can answer right now the question, why not GLN, why only GL2? There is no direct path from GLN to classical problems to solve, but nevertheless, GLN is used indirectly to improve the working conditions in GL2. I mean, via improving estimations for the small eigenvalues, for example, using lifts and other things. Yeah. So here, don't take it literally. This determinant equation is a raw material. I mean, you have to do many other things before you really come to GL2 theory for congruence group. But that's the point where it enters. You see, it's just, I would like to really stress again, like Alan Kohn said in his lecture at the very end, you know, you should really think of, that's a secret of success, to apply the adequate analysis to a problem, and finding that is a halfway to solve the problem. You see, and what does mean adequate is hard. Now, he said that, for example, one shouldn't use polar coordinates to count points of a lattice. I can't agree more with that. Here's the situation the same. You shouldn't use the GL1 harmonics to study primes beyond Riemann hypothesis, in a way. Okay, so quickly about some other applications of modular forms. So I have only 10 minutes left. So one of the interesting things recently happened is that the roots of quadratic congruences modulo primes are equidistributed. You know, when you fix characteristics, only there are two roots, but when you start changing characteristics, they vary, and they vary uniformly. So that's one thing using modular forms. And another interesting thing is the integral points on the sphere. Here is an example how counting on special varieties is very sophisticated and leads to many other problems. Take the ternary quadratic forms with sums of three squares, and the number of representations is denoted by R3 of n, and this is essentially for special n's. Gauss determines which n's are represented. Let's take those without even defining them here, and then this is really the total number of representations is essentially a class number of quadratic field of q of square root of minus n, and then using Ziegel's theorem actually get a lower and upper bound, so the number of representations is about n to 1/2. However, when n is represented, there are not many representations, but some. And you may ask a question whether these points on the sphere are equidistributed. And indeed, using spectral analysis this time on positive curvature surface, the sphere, Duke proved that these points are indeed equidistributed with respect, of course, to the invariant measure on the sphere. And I mentioned that because it's a good transition to the other thing that I want to say. By equidistribution, you can understand what I mean, right? Just simply take this test function g, sum over the points on the sphere, normalized by the total number of points, and it has to be asymptotically equal to the integral. The whole thing is that the very sums from the equidistribution theory for such a problem are really the theta series weighted for this quadratic form and weighted by spherical polynomials, and we know from that these are cusp forms. So actual of 3/2 weight plus h is the degree of the spherical polynomial, and of course there is a very sophisticated multiplier system. This is half inner weight form, and so the problem really reduces to estimation of end coefficient of that cusp form. You see, so now we have a problem estimating end coefficient of cusp form. When the forms, these are holomorphic forms, but with metaplectic on metaplectic covers, I mean the multiplier system there. So the lean does not work here. You know, we still don't have Riemannian conjecture here. So let me just now jump from this to a general context, easier to speak. Take a cusp form of weight k. I remember I pull out the things for normalization, and and there is a convexity bound for such things, which is n to 1/4 plus epsilon. That's a convexity bound. In a moment I explain this why it is called convexity bound. But the point being that it's an irony of Mother Nature that if you really want to have a good result, whatever shallow machinery you use, you are short of the tiny thing that is necessary to get the result. So convexity bound is just too short to prove uniform distribution of points on the sphere. So there's a great motivation to beat the convexity bound. It's not just a sport event on it, but the exponent. And so today we have a little bit better by 1/37 at least. And
137 was last week.
And then so let me explain how this is how does it go to another subject? Yeah. Okay, so this is a metaplectic cusp form, but there is a Shimura map correspondence, the kind of theta correspondence, which sends F to other cusp form G of weight of this weight, but this time it's integral weight, so it is holomorphic molar form, and you can try to estimate. I mean, with a trivial multiplier. But however, what is the relation? So this coefficient satisfies Riemannian conjecture, but what about the original one? Waltzpurger determined that the square of the coefficient of the half-inner weight form is essentially central value of L function of this Shimura corresponding cusp form G, twisted by this real character chi n. And the exact constant here was determined by Zagier and Konen, which is in some applications, it's very important to know exact value of C. Anyway, so we got here a central value of L function. This is the L function. And so estimation of AFN reduces to bounding L function. Wow. So now we are going to L functions. And if you assume Riemann hypothesis of let's say this way first, there is a functional equation there, and using functional equation fragment linear of convexity, you get this bound, and then the coefficient by Waltz-Bourget is half of that, so n to 1/4, and boom, we missed the improvement. So it's too bad that so many structures are used and still miss the things. Okay, and of course the Riemann hypothesis would yield the things, but now it's a different territory which we in a moment come. So a few words how to get bound, how to beat the convexity bound. There's a technique which is very successful in many other situations, which we call amplification method. The idea is don't and this is a great point everywhere. Peter, I think, will make even much clearer presentation of the idea of families of L functions. So don't look at one L function. There's not enough structure there. Look at a proper family of functions and self-dual. That means if L functions attached to each element of that family satisfy functional equations which for the same f, and they have all a product. For every of such f in the family, we have a conductor, call it analytical conductor. It's a number which appears in the functional equations like this. And then again, by fragment linear convexity, you get a bound for the L function, Cf to 1/2. That's why it's called convexity bound, because of fragment linear principle. But the point is that if you take a large family of L functions, and suppose it is in some mystic sense, spectral sense, complete. I have no time to say what it means. But if it's complete, then when you average over the family, you have a dual side of it. It's like explicit formula between primes and zeros of L function, but a bit different. So this is the nature of the things. When you sum over the family of such Balna form, you get a diagonal symbol and then some off-diagonal terms. Example, if you take just the normal basis of cusp forms for that group, here then we end up with the Peterson formula. And so these off-diagonal terms are really Klosterman sums here and Bessel function. Okay, and when you apply this formula to estimate the second pi moment of the L function on the critical line, you get this bound. You can't get better than that, because remember, f, the number of elements in f is the number of elements of f, right? And this cannot be better than Riemann says, the linear hypothesis. So that's the best possible bound. And again, when you drop by positive everything but one term, you get this bound. And it happens that the conductor usually is as large in the naturally selected family as large as the cardinality, you see, because of the completeness requirement. So if you take a smaller family, you won't be able to handle this estimation. So again, you just come up again with the convexity bound only. And so the idea is to use amplification. That's my last transparency before speculation of Riemann hypothesis, which I postpone. So the idea is this. Here is the cell function, the same as before, in average over the family, but attach here a small, short linear form in these eigenvalues, and amazingly enough, you still be able to estimate properly with the right order of magnitude that object, if L is not too large. The new phenomena appears here, which is a very great point I have no time to mention, the off-diagonal terms. You have to, in order to get that, the off-diagonal terms appear. Sometimes they are determinant equations, sometimes there are sums over CM points, and there are many other circumstances. So off-diagonal terms is a great slogan today, and what is there? How life looks off the diagonal, the zone of the diagonal. And Riemann hypothesis cannot even penetrate there. So there is many interesting subjects to investigate in future that are not really related to Riemann hypothesis, or not given by Riemann hypothesis, but related in some other way. And again, I'm sorry, I just have no even time to speculate, which is lovely subject to speculate about, twilight zone of diagonal. This is where new structures appear and not controlled by Riemann hypothesis at all. So anyway, you just do this somehow. Just take my word, read my lips, so to speak. And if L is not large enough, it's not an easy result. And anyway, and now just given F, now you are focusing on one F. Choose your complex coefficients in such a way, if you can, of course, not always it's possible, that there's no cancellation here, so the sum will be about L. In the same time, think of this as being bounded, the L2 norm of this is also L. So here, on the left-hand side, for this particular F, of course, this is as large as L squared, when the L2 norm here is L. So you really are putting some weight, highly arithmetical constructed weight. It's not just a test function with Schwarz class or whatever. It's very important that we have here multiplicativity of these eigenvalues to play with. So the contribution on the left hand side is larger of this particular one than the left hand side. So you gain this L factor and beat this way convexity by that much. Yeah, so thank you very much.
Set the new standards for finishing on time. So for once, there is room for questions, if there are any. Don?
Yes. How much time is there? 2 minutes? 3 minutes? No.
You may start 5 minutes and finish the discussion.
Yeah.
Only 10 seconds, huh?
Yeah, maybe. No, I would love to, but maybe I'll be misunderstood if I just start. But on the other hand, it would be really continuation of the set because it's well prepared for it. The context in which I'm going to speculate is related to the families of L functions. And I don't know. I mean, if I have a little bit more time than 3, I'm just they all can talk in the discussion, maybe. You see, because but let me just before you forget, after 2 hours, that the whole thing is actually related to this average over families and completeness of families, adequate functions, etc., etc. So that. Pardon?
If you just put one little lemma.
Yeah, that's a typical situation. You just need one lemma. Yes. No, but the whole thing. Yeah. Okay. So maybe in the discussion I'll be more free to speculate this. But maybe I should say other things here at the end. That the fact that we are using modular forms is by no means essential in analytic number theory. I'd like to emphasize that there's a future of using other structures, other harmonic analysis, etc. My point is that we are really practical people in analytic number theory, and we want results. And so GL2 theory is so well developed beyond all just simple, structures or here and there, that we know much more and that we can do something. So I think I do feel that GLN has a large, great future, but for younger generation, I think. But it's not yet matured enough. The fact that we know the basic structures, or hypothetically, like Langland's program, functoriality, like that, this is really not for analytic number theory. Analytic number theory needs effective and you have to touch the things. You have to have uniformity in parameters that are involved and understand the spectrum. The determinant equation which I mentioned, for example, appears in many problems, but there are other equations that appear in many problems. However, they are not interpreted as kind of determinant equation GLN. I mean, they do appear there, but in a very small corner. So the spectrum, somehow, the spectrum in GLN is too large to single out the object that we want. So that means the family that we're doing is just too large. You see, and GL2 is a perfect match for that. That we got as much as we could, from GL2, because the balance between between the families, conductors, and other things is perfect.
Okay, I suggest we defer the other questions to the discussion session.